Hello, this is lecture 5 of nkaizu's Introduction to Econometrics Theory course. In this video we'll be talking about estimator variance. As always, we'll start with the big picture, but in this video we're going to focus on the second question, the one in red. Why is OLS usually our favorite method of linear regression? So here we have illustrated the linear regression process. In the top right hand corner we have the true population model with the unknown beta 1 and beta 2, the population parameters that we are trying to estimate. In the top left hand corner we have the regression line, which represents our estimate of the true population model. In this equation we see the betas have little hats on top to signify they are from a regression equation. In between the true population model and regression line we have the process by which we go from right to left, from one to the other, which is first by sampling to get our sample with xi's and yi's, and then by doing linear regression on our set of data on our sample, we get a regression line, our straight line of best fit. To start with, a caveat. In econometrics we tend to focus on beta 2 hat rather than beta 1 hat, because usually we are more interested in the slope than the intercept. However, what we are about to say applies to both beta hats. So back to the diagram. We say that beta 2 hat has a distribution. Now clearly we have our sample data, and then we use our regression formula, and then abracadabra we get a number, an estimate for beta 2. Why then are we talking about a distribution? How can a number have a distribution? Well, of course all our calculations to get this number, to get this beta 2 hat, are based on the sample we took. But our sample is usually just a small part of the population. Therefore, the number you get for beta 2 hat depends upon what sample you got. To return to our university campus example, imagine you are trying to calculate the average height of students at your university. You find it infeasible to measure the height of everyone at your university. There's just too many people and too little time. However, the sample you take is representative. Hopefully, but of course there is always a chance that it is not. You could be unlucky and pick a disproportionately high number of tall people. Perhaps you inadvertently chose the basketball team, or maybe you picked again by chance a lot of short people. Therefore, what number pops out at the end when you punch the data into the beta 2 hat formula depends upon what sample you got. And therefore beta 2 hat could be a high number or it could be a low number, but most of the time it's probably somewhere in between. This gives us a bell curve like shape, like the one we see here. When it comes to choosing an estimator, there are two qualities we like. One is that the estimator beta hat is on average correct, i.e. on average equal to beta 2, i.e. the peak of the bell curve coincides with the beta 2 value. So sure, sometimes we overestimate, sometimes we underestimate, but on average we're right on the money. The second quality we look for in an estimator is that